You should not exist. Not you and me. Not this world with all its splendor, including the many mysteries we are trying so hard to solve. There should be nothing. The universe on which the great drama of life unfolds shouldn't be either. But let's go back to the very beginning, to the moment of the Big Bang. The probability of the occurrence of this incredible event is so small that it simply seems absurd. This probability, equal to 10 to the 10th to the 123rd power, was first arrived by the eminent British scientist, Nobel Prize winner Sir Roger Penrose. Penrose's number demonstrates the incredibly high level of organization and precision with which our universe was created. However, the laws of thermodynamics indicate that this order must break down over time. Just as old objects and buildings left unattended gradually decay and become ruins. So the universe itself is subject to a process of gradual destruction. Penrose suggested that black holes play a key role in this process, accumulating chaos and disorder. Scattered throughout the universe are elementary particles that have not yet been absorbed by black holes, indicating the gradual disruption of its original order. Our universe resembles an ancient artifact, a dinosaur skeleton that has not yet had time to crumble into dust. Roger Penrose. It is from this analogy that Penrose concludes that entropy was low in the early universe, with a probability of 10 to the 10th to the 123rd degree. There are many impossible numbers in the world. For example, the amount of antimatter. Of the vast number of particles of ordinary matter that currently exist in the amount of 10 to the 80th degree, only a small fraction are antimatter particles. Antimatter is, at first glance, almost indistinguishable from ordinary matter, except for its mirror quantum properties. However, when a particle meets an antiparticle, they annihilate, turning into energy. If the Big Bang had produced equal numbers of particles and antiparticles, they would have annihilated each other, instantly, leaving the universe empty. Yet the universe seems to have favored matter over antimatter, ignoring antimatter, even though our best theories suggest an equal number of particles and antiparticles were generated at the time of the Big Bang. According to this logic, everything should have been annihilated, and no planets, stars, us, or even this video should have existed. But there is one prediction that is much more troubling to physicists: the mass of the entire universe. If you appreciate the content, please show your support by liking, subscribing to the channel, leaving a comment, and sharing this video with your circle. Your engagement greatly aids the algorithm. By juxtaposing quantum mechanics with the general theory of relativity, two of the most significant physical theories, scientists have concluded that at the moment the universe was created, it should have sunk into nothingness, ceasing to exist before it even began. It should have been crushed under its own weight, much of which would have come not from the planets and stars that populate modern space, but from empty space, from the vacuum. Thus, all of space would have to shrink under the weight of nothing. This mystery, known as the problem of the cosmological constant, has occupied the minds of scientists for a century. How do nuclear bombs work? How can coffee in a cup affect an entire galaxy? Why isn't the vacuum empty? How does the universe expand? And finally, why do we exist in this particular universe? Bloodletting, despite its historical prevalence, is regarded in modern medicine as a questionable and even harmful manipulation for patients. In the past, however, it was a common practice. Julius von Meyer, working as a ship's doctor several centuries ago, frequently used this method of treatment. During his voyage to the Dutch East Indies, von Meyer made a discovery that changed his view of the nature of blood. Under the bright sun of Indonesia, he noticed that the venous blood flowing out during bloodletting was the same bright red color as arterial blood. This surprised the doctor, because in his native Germany, where the weather was cool, his patient's venous blood was always darker than blood from the arteries. Von Meyer speculated that the difference in blood color was related to the amount of oxygen used by the body in digesting food. Sailors in the tropics received more solar heat than those in Europe, which probably increased the oxygen content of their blood and made it lighter in color. This observation led von Meyer to believe that the heat released during digestion was equivalent to the heat received from the sun. He concluded that heat was simply a form of energy. This concept opened new horizons in understanding nature and energy. But what is energy, and what does it have to do with the mass of the universe and the problem of the cosmological constant? The most valuable resource for human beings is not material goods or even time, but energy. We need energy to move, to heat ourselves, to entertain ourselves, and of course, to watch this video. Von Meyer realized that energy can manifest in many forms, and his discovery inspires us to think about the nature of energy and its role in our world. Energy cannot be created or destroyed. It can only be transformed. In this eternal dance of transformation lies the essence of existence. Julius von Meyer. In the 18th century, industrialists first learned how to convert fossil energy into useful labor that powered machines. Steam engine technology used the chemical energy of coal and converted it into heat energy, after which the machine would be set in motion again. It was Einstein who came to the realization that mass also represents another form of energy. To understand why, we need to think of the cosmic speed limit, the speed of light. Nothing can travel faster than light, which is about 300,000 kilometers per second. The defense against ultra-fast travel is that, as we approach this limit, it becomes increasingly difficult for an object to accelerate. Resistance to acceleration manifests itself in an increase in the object's inertia, which is converted into energy. When a body approaches the speed of light, its inertia tends to infinity, and it will take an infinite amount of energy to overcome the light speed limit. If the object stops, its inertia becomes equivalent to its mass. Thus, mass and energy are equivalent. Einstein enshrined this fact in his famous equation. This equation determines how much energy must be extracted from a certain amount of mass. C, in this case, is a conversion factor equal to the speed of light. Because of this coefficient, we realize that a small amount of mass is equivalent to an enormous amount of energy. A small dog weighing about 9 kilograms contains the energy equivalent of nearly a quintillion joules. That's about the same amount of energy released when the Krakatoa volcano erupted in 1883, killing nearly 37,000 people and destroying another 150 cities. This amount of energy can be released through nuclear fusion, where a small amount of mass is converted into a huge amount of heat. This process occurs inside thermonuclear weapons, when hydrogen isotopes combine to form heavier elements with a loss of total mass. The same processes occur inside the Sun, which powers the Earth and other planets in our solar system with its radiance. The conversion of mass into energy is one of the most powerful manifestations of the force of nature. Mass and energy are intertwined in the fabric of the universe, each but a different manifestation of the other's essence. Albert Einstein. Once Einstein realized that mass and energy are equivalent, it dawned on him that gravity must carry to itself not only mass, but any other form of energy. It is for this reason that gravity can attract light, which has no mass at all. And when physicists puzzle over the mass of the universe, they also include all the energy it stores. Energy, hiding in stars and planets, walking around in the radiation that fills outer space. But this is only a minuscule part of the entire energy flow of the universe. Most of the vastness is taken up by a mysterious dark source known as dark energy. In the ancient city of Syracuse, in the 3rd century BC, Archimedes pondered the size of the universe. Syracuse is on the east coast of Sicily, surrounded by sandy beaches on one side and the Mediterranean Sea on the other. Archimedes believed that there was so much sand in the surrounding areas that it must be everywhere on the planet, and the amount simply could not be counted. This prompted Archimedes to ponder how many grains of sand could fit in the universe. His musings were called the Samet. It all started with a poppy seed. Stacking the seeds side by side, Archimedes noticed that every 40 seeds made up one Greek dactyl. That is, the width of a finger, approximately 18.5 millimeters. Within each seed, Archimedes envisioned a multitude of grains of sand. The largest unit available to his thinking was the myriad, equal to 10,000. In order to calculate the number of grains of sand in the universe, Archimedes had to invent a new counting system and also to estimate the universe. According to him, the universe extends to a cluster of fixed stars, bound to a dome that forms a huge sphere centered around the sun. Using clever but crude estimates, he estimated the diameter of this sphere to be 100 trillion Greek stadia, that is, about 2 light years. According to this logic, the The universe is unable to contain an infinite number of grains of sand. In reality, this number does not exceed 10 to 63 degrees. And how much does such a universe weigh? Archimedes did not answer this question, but we can do so. Let's assume that the weight of 1 grain of sand is about 10 milligrams. Then, if Archimedes' universe were filled with sand, its weight would be about 10 octodecillion kilogram. Of course, the size and mass of Archimedes' universe are crude approximations, made up hastily, and they are far from the truth. Archimedes grossly underestimated them. When we talk about its mass, what we really mean is how much energy it contains. To know how much energy all these components represent, we need to understand what is meant by the term universe. By this term, we mean the visible universe, the part of the universe that is observable. Contrary to its age of 13.8 billion years, this period is not long enough to receive signals from the most distant regions of space. However, the main limitation is not the distance to most of the objects in the universe, but its expansion rate, which causes the light signal to be displaced by the wave of cosmological expansion and unable to overcome the speed of their removal. It may seem that the apparent size of the universe should be about 13.8 billion light-years. However, taking into account the described expansion effect, the size of the observed universe is 46.5 billion light-years, leading to an estimate of the edge-to-edge extent of about 93 billion light-years. It is important to note that there is no huge cosmological wall at the edge of the observed universe, leaving open the possibility that the true structure of the universe may be infinite. Current astronomical evidence confirms that our universe has a Euclidean geometry, where space is a plane, which in turn means that light does not undergo distortions when traveling great distances. Consequently, scientists suggest that the diameter of the entire universe is at least 23 trillion light-years. It should be noted that estimating the total mass of the universe is a non-trivial task, since most of its constituents are beyond our direct observation. Suddenly, the universe, hidden billions of light-years away from us, is filled with Archimedean grains of sand, or maybe there's nothing in it at all. So we'll weigh only the observable universe. Let's start with the stars. The most typical star that serves as an object of study is the Sun. Its mass is on the order of 2 nonillion kilograms. Through observation, it has been found that there are between 100 and 400 billion stars in our galaxy, whose total mass reaches 10 to the 42nd degree of kilograms. Given that there are at least 200 billion galaxies in the observable universe, each containing an average of 100 billion stars, the total number of stars in the universe could be at least 20 sextillion, with a total mass of 10 to the 48th degree of kilogram. This number seems truly gigantic. However, it is worth noting that stars make up only a small fraction of the total mass of the universe, as the bulk of the mass is in the interstellar gas. To estimate the mass of the universe more accurately, it is necessary to study its effect on the structure of space-time. Through observations of cosmic microwave radiation, otherwise known as the relic background, researchers can study the continuous stream of primordial photons left over from the formation of the first atoms, some 380,000 years after the Big Bang. These photons, having traveled vast distances through the universe, reach us from a variety of directions. They can even be detected among the interference on analog television. Using space observatories, astronomers measure the temperature of cosmic microwave radiation in different regions of the celestial sphere. By analyzing variations in temperature and background, scientists can reveal the effects of matter, radiation, and other forms of energy on the structure of space and time, and trace the composition of the universe. The cosmic microwave background, combined with other research techniques, indicates the presence of approximately 150 sextillion kilograms of matter in the observable universe, equivalent to 1.5 with 53 zeros. This is only 5% of the total energy concentrated on the surface. In addition to the ingredients discussed above, there are 2 other components that make up the bulk of the energy composition of the universe. First is dark matter, which is similar to the ordinary matter from which stars, planets, and you and I are formed, but is invisible. It does not interact with electromagnetic radiation, and light passes through it without obstacles. In addition, humans can pass through dark matter without physically feeling it, except for the effects of its gravitational field. Dark matter has mass and energy, just like ordinary matter, and therefore has an effect on the structure of space-time. Although there is 5 times more dark matter than ordinary matter, it does not dominate the energy balance of the universe. Dark energy has a much more significant presence in the cosmos, accounting for a whopping 70% of the total energy content of the universe. Dark energy represents another invisible component, responsible for the accelerated expansion of the universe. We see this expansion when we study the light coming from distant supernova stars. An interesting phenomenon is that they appear less bright than expected. But what really constitutes dark energy? Analysis of the data suggests that there is an unusual substance with an almost constant energy density throughout the universe. And as you'll realize later in the video, it's exactly what you'd expect from empty space, a vacuum whose energy density is also constant. The void, as it turns out, is not quite empty. In fact, the vacuum is a constantly simmering broth of virtual particles that appear and disappear so quickly that they can't even be seen. These particles contribute significantly to the energy balance of the universe. At the beginning of the era of quantum mechanics, most scientists called this zero-point energy. Nowadays, it is known as vacuum energy or cosmological constant, denoting the same phenomenon. The total energy of regular matter, dark matter, and dark energy is equivalent to 67 times 10 to the 60th degree tons of TNT. That's how much the universe weighs. The sheer amount of mass is offset by the gigantic scale of space. Energy is evenly distributed throughout the volume of space, and the average density becomes very low. Despite the enormous power of dark energy, its concentration is so low that you can fill an entire swimming pool with it, but not enough to crush even a fly. And this is good because it is thanks to the low density that the universe has been able to exist until now and take its present size. However, when studying the universe, we are faced with one of the greatest cosmological mysteries, the problem of the cosmological constant. Why is the dark energy density so low? In the most convincing and tested physical theories, we find that the energy of the vacuum must be absolutely enormous. According to these theories, our universe should not have evolved as smoothly as we see today. Instead, it should have been born as a supermassive blob that would have immediately exploded under the gravity of the vacuum. The universe should never have become so vast and mature, should never have created the conditions for intelligent life to arise, and it should never have had you. However, the fact remains that the universe exists as we see it today. The truth turns out to be that the universe is much lighter than advanced theories have suggested. The question is, why is there so little dark energy in the cosmos? Where does all the vacuum energy stay? Why hasn't it destroyed the universe? To answer these questions, we have to go back 100 years to the city of Hamburg in Germany. At that time, Hamburg, as if reborn from the ashes of the First World War, turned into a bustling metropolis, attracting the best minds of its time. In the center of the city, next to the Elbe River, there was a lake known as Ulster. It was by its shores, in a cafe, that 2 physicists, 2 comrades, sat together. The first man, Otto Stern, led a luxurious lifestyle, indulging in pleasures without much restriction. Sometimes he came to Vienna just to have a good meal. In contrast, Wolfgang Pauli led a very different life. At the time of their meeting, he had a black eye from a fight in a local bar the night before. Despite this, Pauli listened intently as his friend Stern argued that zero-point energy was not really zero-point energy. Stern had performed calculations of the effect of vacuum energy on the vapor pressure of neon isotopes. However, Pauli remained unconvinced by Stern's account. Using a napkin and ink, he hastily scribbled a text to verify his calculations. His conclusion was that if the vacuum energy were not zero, the universe could not expand even to the moon. Think of the vast universe around us, filled with stars that light up the cosmos, from red giants to dwarfs. Orbiting planets, whether solid or not, span the temperature spectrum and are home to various elements, from the periodic table. On a planetary scale, these celestial bodies are enveloped in picturesque gas clouds. Each constituent has mass and energy in one form or another. But suppose someone vacuumed the universe, collecting everything from stars to bacteria to atoms. What's left, what remains, is a quiet emptiness. It would be naive to think that it is devoid of weight and energy. According to quantum theory, even empty space contains energy. It cannot be devoid of it. Back in 1911, the famous German physicist and founder of quantum mechanics, Max Planck, pondered the concept of quantum tunneling. And shortly after him, his own compatriot Walther Nernst wrote, "In the depths of emptiness lies the untapped reservoir of boundless energy, for the vacuum is not a void, but an exotic medium, teeming with latent potential, awaiting the touch of human ingenuity to unlock its secrets." Another notable German physicist, Albert Einstein, held a significant interest in zero-point energy. It was Einstein who initially introduced the concept of a cosmological constant in 1917. His rationale stemmed from the necessity for a repulsive force throughout space to counteract the compressive effects of gravitational forces. Einstein advocated for a static universe, one that neither expanded nor contracted. However, the equations derived from his own general theory of relativity indicated a universe that should contract. To address this, Einstein, along with Otto Stern, proposed the inclusion of a force opposing compression, embodied in the form of a cosmological constant. Eventually, Einstein renounced this notion, dubbing it his greatest blunder. He asserted that no theoretical physicist could contemplate vacuum energy without a sense of embarrassment and irony. Nonetheless, Einstein's intuition proved correct when the concept of zero-point energy gained recognition in the mid-1920s. That's when the German physicist Werner Heisenberg entered the scene. In the summer of 1925, afflicted by a severe bout of hay fever, he sought refuge on the Helgoland archipelago in northern Germany. Away from urban life and the triggers of his allergies, he delved into contemplating the behavior of hydrogen atoms and their spectral lines. One restless night, a revelation struck him, unveiling the enchanting realm of quantum mechanics. He grasped the origin of vacuum energy. To elucidate, let's consider a simple analogy. Imagine a ball placed at the bottom of a bowl. As it settles, it appears to be at rest. But is it truly motionless? Can we precisely determine its position and velocity? No, because the ball still interacts with air particles, which exert pressure on it. Now, imagine removing all the air and cooling the ball to absolute zero. Would it then come to rest? Anticipating ahead, many might say no, and they would be correct. The ball would continue to exhibit fluctuations. Heisenberg arrived at this insight when he recognized the inherent uncertainty in such scenarios. In the pursuit of truth, we must accept that there is always some uncertainty, for it is in the gaps of our knowledge where the most profound discoveries await. Werner Heisenberg. Quantum mechanics is like roulette, where scientists deal only with probabilities. The more precisely the position is determined, the less precisely the momentum is known in this instant, and vice versa. Thus, knowing the position of a particle, we don't know its velocity, and vice versa. Thus, the ball is forever oscillating at the bottom of the bowl. Heisenberg's uncertainty principle states that everything in the microcosm must remain in motion. What does this have to do with our empty universe, devoid of all matter? Before it was purified, it was teeming with various elementary particles, folding into increasingly complex structures. However, these particles are essentially ripples in the fundamental fields of nature. Photons are ripples in the electromagnetic field. Gluons are ripples in the strong interaction field, and the Higgs boson is a ripple in the Higgs field. Essentially, the cosmic janitor seeks to cleanse the universe of these ripples, leaving behind a serene homogeneity and creating a perfectly flat spacetime. However, as we know, this attempt has not been successful. The uncertainty principle states that even in a vacuum, fleeting quantum fluctuations persist as perturbations. But if there are no diverse particles in the universe, then what fluctuates? What is this mysterious janitor hidden substance? This substance is represented in the form of so-called virtual particles, which appear and disappear so quickly that we do not even have time to detect them. However, they are subject to fundamental constraints. These cascades of virtual particles resemble a seething broth pervading all of space. While we cannot discern the individual bubbles comprising this broth, collectively, they impart non-zero energy to the vacuum. But how relevant is this energy? A captivating microscopic illustration is the gecko, with its remarkable ability to traverse walls and ceilings, seemingly defying gravity. Scientists attribute this feat to vacuum energy. The unique microscopic structure of the gecko's legs contributes to their apparent adhesion to surfaces without being glued or suctioned. This phenomenon is a manifestation of the Casimir effect, named after the Dutch physicist Hendrik Casimir. As surfaces draw close, the Casimir effect becomes discernible enough to be quantified. This alteration in vacuum energy gives rise to van der Waals forces between atoms and molecules. Notably, these forces underpin the gecko's remarkable wall-walking ability. With the acknowledgement of non-zero vacuum energy, it becomes imperative to assess its impact on the universe. When Wolfgang Pauli conducted his calculations in a coffee shop in Hamburg, he effectively fragmented the entire universe into pieces, each with sides measuring approximately 1 femtometer. This scale aligns with the classical radius of the electron, representing the limit of experimental physics at that time. By segmenting space into such minuscule components, we gain insights into the particles' positions within each segment. However, we forfeit information regarding their momentum. This implies that we lose some of the energy in our overall estimation. As we divide space into increasingly smaller segments, the virtual particles exhibit progressively higher energy. Following Pauli's reasoning, each segment would harbor a minuscule fraction of a joule, seemingly insignificant at first glance. However, the sheer quantity of segments is staggering. In the empty coffee cup that the scientist emptied, there would exist an astounding nonillion joules of energy, equivalent to 10 to the 30th power. This amount of energy is sufficient to vaporize all the oceans on Earth. But physics didn't halt there. Centuries later, with advancements in technology, we've gained the ability to delve deeper into the microscopic fabric of the universe. Nestled beneath the Swiss-French border lies a marvel of engineering, the Large Hadron Collider. This colossal machine recreates the primordial moments of the universe by colliding subatomic particles at velocities nearing the speed of light. It provides unparalleled insights into the microcosm, fragmenting the universe into segments 10,000 times smaller than the electron-scale divisions envisaged by Pauli. On the scale of a hadron collider, the energy contained within a coffee cup is sufficient to obliterate all the planets in the Milky Way. Indeed, the energies amassing in space are potentially far more immense than we currently comprehend. Our limitations lie solely in our ability to probe the quantum realm. How far can we push these boundaries? One can envision the universe fragmented into pieces as small as a Planck length, approximately 1 trillion times smaller than the scale achieved at CERN. The Planck length is the distance at which the structure of space and time ceases to make sense as it becomes overwhelmed by quantum effects. This concept bears resemblance to adjusting graphics settings in a video game. As you zoom in, details become increasingly intricate, yet at a normal scale. Textures are optimized to prevent overwhelming the system. In this scenario, a coffee cup would contain a staggering Google gigajoule of energy. This amount of energy is sufficient to repeatedly obliterate every planet and star in the observable universe for a quintillion time, equivalent to 10 to the 48th power. Does the fact that empty space everywhere hides such gigantic energies, even inside your body, horrify you? In a universe devoid of gravity, where vacuum energy remains uniform everywhere, there's little cause for concern. This uniformity is why we refer to it as the cosmological constant. To start using it to destroy whole galaxies, you need a gradient, a difference in energy density. Without gravity, there are no gradients. But in our universe, there is gravity, and that's a different story. Here lies the crux of the issue with the cosmological constant. To comprehend it, we must grasp the workings of gravity. Since Einstein's era, we've recognized that gravitation differs significantly from other fundamental forces. It's not merely a force, but rather the curvature of space-time itself. Consequently, any form of energy, not just mass, can influence this curvature. Vacuum energy is no exception. Greater the energy, the more tangible its effects on the fabric of space-time. Wolfgang Pauli's assertion that the universe shouldn't have expanded to the size of the moon's orbit stemmed from his understanding of vacuum energy, limited by the experimental physics of his time. However, modern estimates indicate that the universe contains so much energy that it should have collapsed under its own weight, long before reaching even the tip of your nose, let alone the moon. But what has to be said is that the universe is billions and trillions of times farther away than the moon. The edge of the observable universe, as mentioned at the beginning of the video, is about 46.5 billion light-years away. And if the cosmological constant exists, it is much smaller than we would expect. The energy density, the vacuum, must be 120 orders of magnitude lower. The energy contained in a coffee cup would not even be enough to swat a nut, let alone destroy a planet. Yet, authoritative theories of fundamental physics suggest that the universe must be filled with so much energy that it must collapse. This conundrum is known as the cosmological constant problem. But what is the cause of this? Let's transport ourselves to Semipalatinsk on August 29, 1949, at 7 a.m. local time, when the first Soviet atomic bomb was detonated. This historic event was witnessed by 8 people, including Yakov Zeldovich, head of the theoretical department of the Nuclear Development Center. Zeldovich, a legendary physicist who played a key role in the Soviet nuclear weapons program, continued to make significant contributions to particle physics and cosmology, even as Robert Oppenheimer, his American counterpart, passed from the public eye after his involvement in the development of the nuclear bomb. Yakov Zeldovich's brilliance illuminated a vast array of scientific disciplines, from fluid dynamics to cosmology, leaving an enduring legacy that continues to inspire generations of physicists. Stephen Hawking. In 1967, Yakov Zeldovich reignited global attention towards the cosmological constant problem. Unlike the era of Pauli, Zeldovich's time offered theoretical physicists a much broader toolkit, notably including general relativity and its applications to cosmology, as well as quantum theory to describe the subatomic realm. Zeldovich was the first to recognize that the vacuum must be a dynamic milieu, teeming with virtual particles. Moreover, he sensed that our understanding of the universe was incomplete, emphasizing that resolving the cosmological constant conundrum would be pivotal for particle physics. Perhaps, Zeldovich speculated, the issue lies in our empirical approach. Maybe the energy of empty space varies depending on what and how we measure it. Why should we listen to Pauli's spontaneous musings about the energy of a coffee cup? It's conceivable that nature is playing a cosmic joke on us. However, discarding the accumulated and thoroughly tested ideas of the past century is not a viable option. We possess a rigorously validated theory of relativity, which has accurately predicted phenomena such as gravitational lensing around the sun, the detection of gravitational waves via laser interferometers, and the precession of Mercury's perihelion. Likewise, quantum field theory offers precise descriptions of processes within the microcosm. The conundrum of the cosmological constant represents a profound crisis in our understanding of fundamental physics, as recognized by Yakov Zeldovich over half a century ago. It signifies a gap in our comprehension, something of utmost importance yet elusive. Resolving this enigma is anticipated to unveil profound insights, akin to a 7-mile leap toward a genuine understanding of the universe's mechanics. Similarly, perplexing is the information paradox, in which Zeldovich also played a role. What fate befalls information entering a black hole? Does it vanish, thus defying the laws of quantum mechanics? Or does it endure? And if so, how is it preserved within the black hole's grasp? Resolving these intertwined dilemmas promises to propel our understanding of the universe to a qualitatively new level. A common theme underpins these puzzles: the recognition that calculating the cosmological constant represents merely a piece of a grand puzzle. Elementary particles likely contribute significantly to vacuum energy, hinting at the existence of hidden constants, counterbalancing the vacuum's crushing potential. This analogy is akin to comparing the weight of all stars in the universe to the mass of a single electron. One prevailing theory to reconcile these complexities involves the notion of a multiverse, positing that our observable universe is but one among many potential universes, each possibly governed by different fundamental constants. Another candidate for solving the cosmological constant problem is string theory, where there is the option of the existence of 10 to the power of 272,000 different vacuums and universes, with their own energy level and spectrum of cosmological constants. This plethora of possibilities raises the intriguing question: how did we find ourselves in a universe with such a minuscule cosmological constant? Here, the anthropic principle comes into play. This principle posits that most universes are inherently unsuitable for the emergence of life, and we find ourselves in the universe where all the necessary conditions for intelligent life coincidentally align. If the cosmological constant was significantly larger, the universe would have collapsed prematurely. Conversely, if it were too small, the universe would expand at a slower rate and eventually contract before intelligent life could emerge. Thus, only in a universe like ours is there a possibility for the emergence of intelligent beings capable of contemplating and potentially resolving the cosmological constant problem. In 1997, Nobel laureate Steven Weinberg proposed that if vacuum energy accounted for less than 60% of the total energy content of the universe, anthropic arguments would fail to explain its smallness. Remarkably, less than a year later, astronomers announced the discovery of dark energy, which comprises approximately 70% of the total energy budget of the observable universe. This discovery bolstered the validity of the anthropic principle. So let's understand what the anthropic principle is. Throughout the history of mankind, its view of its place in the universe has undergone significant changes. In ancient times, people considered themselves to be the center of the cosmos and the entire universe, to revolve around them. With the development of science, however, this egocentric view was shattered, and mankind found itself just a speck drifting in the vastness of space, one of countless worlds in a sea of galaxies. In recent years, these disparate views have converged into a single concept known as the anthropic principle. This principle recognizes humanity's seemingly insignificant position in the cosmos, while acknowledging the amazing circumstances that have allowed life to flourish on Earth. In 1543, Nicolaus Copernicus published his groundbreaking treatise on the rotation of the heavenly bodies, refuting the view that the Earth was the center of the universe, and arguing that this central position was occupied by the Sun. Copernicus's revolutionary ideas paved the way for a new understanding of humanity's place in the cosmos, aligning our abode with the other planets. His example was followed by Giordano Bruno, who paid with his life for the idea of a plurality of worlds. More than 5 centuries later, we know exactly our place in the universe, a vast region of space that we can see billions of light years deep, and that consists of typical galaxies with typical stars and typical planets. The ordinariness of man was elevated to a principle that now bears the name of the very scientist Nicolaus Copernicus. In 1973, on the occasion of the 500th anniversary of Copernicus's birth, the International Astronomical Union convened an assembly in Poland, at which ambitious astronomers presented their research. Among them was a young astrophysicist, Brandon Carter, whose presentation made the audience reconsider Copernicus's ideas and their implications for our understanding of the cosmos. Our position in the universe is strictly certain, because only under such conditions could man have come into existence. Brandon Carter. In essence, Carter argued that our position in the universe, with some adjustments, could be considered privileged because it allows for our existence. When examining the vast expanse of the cosmos, it becomes apparent that most regions are inhospitable to life. Intergalactic voids, black holes, red giants, and other cosmic phenomena create environments where life cannot emerge or thrive. Carter emphasized that life requires specific conditions, and these conditions are rare in the universe. Thus, the Copernican principle, which posits that humanity's position in the cosmos is typical and unremarkable, was supplanted by the weak anthropic principle. This principle asserts the uniqueness of the results of our astronomical observations, suggesting that the universe is tailored to allow for the existence of observers like ourselves. Furthermore, the event also introduced the strong anthropic principle, which goes a step further by proposing that the universe is as it is because it contains observers, namely humans. In other words, our existence as observers influences the fundamental nature of the universe itself. Could it be that the words of the Bible and Descartes were prophetic, and the universe was really created for us? In 1919, mathematician Hermann Weyl determined that the force of electric interaction among charges is vastly superior, by 39 orders of magnitude, to their gravitational pull. This striking contrast in the strengths of these seemingly similar fundamental forces begs the question, why such a substantial difference? During that era, the prevailing belief was that stars sustained themselves through gravitational self-combustion. Essentially, it was thought that a star would simply disintegrate, transforming its substance into energy. However, the predicted lifespan of such stars, in the millions of years, was evidently insufficient. By then, knowledge about the age of the oldest known rocks and the pace of evolutionary processes was already established. It wasn't until 1930 that German physicist Hans Bethe proposed a groundbreaking model of thermonuclear fusion occurring within the stellar cores, providing them with fuel that could sustain them for billions of years. Throughout their existence, stars undergo multiple cycles of fusion, progressing to ever more intense reactions involving heavier elements. The sequence starts with the formation of deuterium, followed by helium synthesis. Helium then fuses into beryllium, subsequently leading to the creation of carbon, oxygen, and other elements essential for life's emergence. It was calculated that if gravity were marginally stronger by a couple of orders of magnitude, stars would burn out so rapidly that habitable worlds wouldn't have time to coalesce around them, and the eventual rise of humanity would be unlikely. The theory of fusion continued to evolve until encountering another significant hurdle. The discovery emerged that the nucleus of carbon, formed through the interaction of beryllium and helium, is inherently unstable and should decay. However, carbon exists, indicating that a solution to this puzzle exists. This solution was unveiled by American physicist Fred Hoyle, who postulated the existence of an unknown channel of interaction between beryllium and helium nuclei. His intuition proved correct when he identified the sole missing excited state of the carbon nucleus, characterized by an energy level of 7.66 mega-electron volts. Even a slight deviation from this resonance energy would result not only in the absence of carbon, but in the disruption of the formation of all subsequent chemical elements. It's worth noting that rocky planets and life itself are predominantly composed of these elements. Yet, was the sequence of events merely a remarkable coincidence? Or is there a deeper significance behind the universe's emergence, finely tuned to allow our existence? There exist 26 fundamental constants governing all processes in the universe, and scientists are intrigued by the consequences of altering their values. For instance, a mere 0.14% reduction in the mass of a proton relative to a neutron would prevent the formation of elements heavier than hydrogen. If the nuclear interaction force were slightly stronger, all hydrogen would swiftly convert into deuterium, hindering the formation of water, a vital ingredient for life. Adjusting the weak interaction's intensity could quell supernova eruptions, preventing the formation of the rocky planet-building elements. Some scientists argue that the concept of fine-tuning might not be as crucial as commonly perceived. They suggest that if you tweak the values of constants in groups, rather than individually, the consequences might not be as severe. Others attribute this finely tuned nature of the universe to the handiwork of a divine entity. Alternatively, some take a more hands-off approach, viewing the universe as a self-regulating system that simply functions without our interference. Why it works is not our concern. Interestingly, the majority of people lean towards this latter perspective. The discussion of fine-tuning often delves into the realm of metaphysics, which makes it a contentious topic. However, scientists endeavor to maintain a scientific approach to the matter. One hypothesis posits that the universe's parameters may vary across different regions or evolve over time, potentially enabling the emergence of life in specific areas of space. Yet, scientists pursue a more straightforward path in search of a fundamental theory capable of elucidating the significance of constants and the properties of all particles. Unfortunately, modern science has yet to reach this theoretical pinnacle. The unresolved conflict between the standard model of particle physics and the general theory of relativity remains a significant challenge. Nonetheless, there appears to be a promising avenue forward: string theory. This theory suggests the existence of a landscape of false vacuum regions, where chaotic expansions give rise to myriad universes with varying properties. Some of these universes may fortuitously possess parameter values conducive to the emergence of observers, while others may not. Since observers are confined to their respective universes, they remain unaware of the existence of lifeless ones. The concept of a multiverse presents a serious problem for discussion because it is largely speculative, beyond our current understanding, and difficult to verify. From a theoretical perspective, however, it offers a potential solution to the dilemma of the anthropic principle. Consider a person who does not know his height, but assumes that he is neither exceptionally tall nor exceptionally short. With 95% probability, his height will be in the moderate range, say between 163 and 190 centimeters. In fact, there seems to be a moderate range within which the values of certain parameters in the universe will not fall with excessive probability, a concept akin to the notion of uniqueness of fit. Notably, not all constants are crucial to the origin of life. Parameters such as neutrino mass or galaxy distribution density, known as bio-neutral parameters, allow for a wide range of values, favoring the emergence of life. Similarly, estimating the age of the universe depends not only on direct observations of the cosmic expansion rate, but also on studies of biogeochemical processes and stellar evolution. For example, during the first 2 billion years of the universe's existence, there may not have been enough time for the elements that form DNA to form. Conversely, after about 100 billion years, most sun-like stars may cease to exist, which would also reduce the chance for humanity to emerge during that period. Thus, the average age of the universe, suitable for our origin, is roughly between 10 and 100 billion years, a range consistent with current evidence. Using the anthropic principle, we can try to clarify other constants whose nature remains unclear. The most egregious case of tinkering relates to the problem of the cosmological constant. But the anthropic principle is still a very shaky concept to rely on entirely. Instead, science is on the lookout for alternative ideas, a vast extra-dimension fractional phenomenon in a vacuum, and others. Right now, the mystery of the cosmological constant is still a mystery. It all started with Archimedes' attempts to weigh the sandy universe. Then scientists weighed all the planets, stars, and galaxies, weighed dark matter, and, as paradoxical as it sounds, the vacuum. And where did this crushing energy disappear to? After all, it should have destroyed the universe in the first moments of its existence. But, as you can see, it didn't happen because we have to find the answer to these questions. We must try to unravel all the mysteries of the universe